hold in here. Okay.
So let me welcome here President colleague Chin-Hui, who I don't need to say needs no introduction, but this is such a awfully used phrase. Of course, she doesn't need any introduction, but still I will do a short one. Because I know him. We met in Santa Barbara in 1983 when he just was a fresh refugee from Verbex, I believe, one of these places which are now in the history, working for a company called Digital Sound, which was trying to make money on recording the telephone. But anyways, at the time he was the first one who tried to teach me HMMs, which he never succeeded, and I never succeeded to learn it really. But I remember him giving a talk, and he sort of thought it's so sophisticated. Then Chin disappeared into Bell Labs, and of course then he made a very distinguished career. He's a distinguished member of technical staff and recipient of numerous awards and so on and so on, and also many papers. And after the Bell Labs, he became a professor at Georgia Tech, where but to my surprise, he still sticks to his speech after all these years. He's one of the original ones. And he will tell us what he is after nowadays. I suspect I know a little bit, but I'm still looking forward to hear what Chin has to say.
Thank you very much, Hinek. How is the recording? Okay, good. Yes. It's nice to be back here again. I was here a few years ago for a summer workshop, and what you will hear today actually is some extension beyond what we did at the workshop. This was also related to an NSF project that a few of us were involved with, but you will see that we are interested in this concept of language universal speech modeling. It has been going on for many, many years. Now, with some of the new modeling tools, I think we can talk more about this area, and many of you probably know about the topic of vector quantization, and we could, of course, we go beyond there. So that's the outline of my talk. I'm going to, again, talk about language universal speech modeling, and then specifically talk about acoustic modeling and phonetic modeling in the sense of something with and without phonetic definitions, and you'll see what I mean. But the most important part is to think about knowledge-based speech units that can be shared among different languages. And you'll see that this is an important notion later on for some of the applications of interest. And then I'll talk about the NSF project that we call Automatic Speech Attribute Transcription, or ASAT. And basically the notion there is to think about bottom-up versus top-down speech transcription. And it involves something called speech attribute dictation, and then something called knowledge integration. Now, it'll become clear later on. And then I'll talk about two new language universal multilingual applications. Specifically, I'll talk about language universal attribute and phone recognition. I think this is a topic of interest to many of you. And then talk about attribute-based spoken language identification. This is in the area, more recently people are talking about modeling something with no resources, meaning modeling a language without language-specific speech data, for instance, and then summarize my talk. So there are a lot of stuff that will be covered in this talk, but I'll try to only touch on some high-level notion and then go deeper into some areas you may be of interest. So the idea of language universal speech modeling is like what I have here, that basically you have a lot of data that may come from many different languages. So this is your overall speech databases. And then you try to go through this notion that I will talk about, something called universal acoustic modeling, and then come up with a set of universal acoustic models. Now this, of course, it depends on how we define some of those units that I will talk about later. And now, if I have those universal acoustic models, then what I can do is that, if I have, for instance, individually linguistic defined events, then I can use my universal acoustic model as tokenizers to transcribe this event-specific data into some kind of spoken documents. Now here I have not defined what I mean by a spoken document, but basically it's just converting spoken utterances into a different domain that we can process later on. For instance, we can do feature extraction, and then we'll have utterance vectors, and this collection will let us do different things later on. Now, so this, for instance, one of the applications could be that you have this overall vector collections here, and then you go through some classified design, then you can define event classifiers for some of the events of interest here. So of course, depending on the event you have in mind, you can design different systems. And one of the events could be a language, then you can have a language identification system. And the event, if it's related to phonetic units, then this could be a phone recognizer or a speech recognition system.
Did you touch the touch screen on the podium?
Ah.
It gets canceled out of the buzz that's coming through the speaker.
Ah.
On the podium.
On the podium here. Maybe someone can help me do that. Ah. Mute. Okay.
It's a mute, and if you do decide to play audio.
Okay.
Nobody works on acoustics anymore.
you have to know what's going on, right? So let's talk about modeling. So I think by now we know the notion of frames. It's been done so many times. We use 10-minute second frames a lot, but a frame can be even shorter. We also know the notion of segments. Segments, of course, are related to a number of frames. But, of course, they can mean different things. So if we go back to, this set of modeling, then, of course, there are some language universal characterization that we are very familiar with. For instance, I think I went back. Is this? Yeah, okay. So if we, started with, I think I talked about this already, but if we talk about acoustic unit to begin with, that means some unit that has no direct linguistic definitions, then we can talk about vector quantization. I think people doing coding and many similar applications that are very familiar with vector quantization. Moving forward from frame using vector quantization, we can now talk about matrix quantization. This is not as well known, but basically you can extend the notion of frame into multiple frames and then talk about, quantizing segments, and that's called matrix quantization. And then if we move beyond matrix quantization, and then we can actually assign models to it instead of just a quantization unit. We can actually assign models. So there's something called acoustic segment models that I will talk about a little bit later. But basically the idea is that if we have segments, then we can model it with any of the modeling techniques that you would like to impose. And so those are units with no linguistic definitions. But once you get interested in some language-specific notions, like for instance, forms and syllables. And of course, we have to link some of the modeling units with linguistic definitions. So that, of course, is something language-specific. But between these two sets of units, we can define another set of units, which is language universal with linguistic definitions. So this is what I would spend most of my effort on. It's something that related to speech attributes, which can be defined language universally. For instance, manners and place of articulation, they are associated with different units for different languages. But the definition on manners and place of articulation is probably more universal to many of us than just the form definition, which can be language specific. So far so good. Attribute is an important thing that we will come back again later. Yes?
Maybe you're going to explain this, but what manner and place of
Okay, yeah, I will do that. So definitely we'll get to it right away. So the notion of this was starting, of course, in the mid-90s at Bell Labs. But then, we were thinking about if there's something can be done differently from how we've been doing, HMM-based speech modeling. But the idea, can be summarized in terms of, can we try to mimic human speech recognition? I mean, what is the notion behind that? And it looks like, many people talk about using so-called acoustic landmarks. I think, we know Dennis Klatt, talked quite a bit for the, during the APA in the mid-70s. And then, of course, we have distinctive features and, phonological parsing. I think Ken is here, but his thesis, if it's already forgotten, actually there are some interesting notions related to what I want to talk about today. But basically the idea is that if we can produce a good enough phone lattice, then you can actually do speech recognition from that phone lattice. And I will go one step further and say if you can produce a good enough attribute lattice, that actually, you can also do speech recognition beyond that. And, I think we can go into discussions about that. But basically the idea, of course, is that we have so much knowledge in speech production, speech perception, speech analysis. What can we, use, what part of the knowledge can we use to help us do speech recognition? And that, of course, goes back to many of you already know about reading spectrogram. How do we read spectrogram? And then if we can, human can do speech, can read spectrogram well and then be able to interpret speech, what's missing in terms of what can we take advantage of if we want to use the knowledge in reading spectrogram to help us transcribe speech. Okay, so, but all this seems to boil down to that we can explore knowledge, speech knowledge hierarchy, and then we can detect acoustic and auditory evidence in speech that will help us do something. We can weigh and combine evidence to form interesting hypotheses, and then after that we can verify them. So all this seems to be pointing to the direction that we have to do some kind of bottom-up knowledge integration in order to do some of this. But many of us also have worked on HMM-based systems that's completely top-down. So there's something there. Top-down is very, very effective for what we do today. So can we combine both top-down and bottom-up? And where do we meet this notion of bottom-up and top-down processing? So this will be, what I will talk about today. So this starts with this project called Automatic Speech Attribute Transcription, or ASAT. So this was an NSF funding for 4 years, and now we extended by another 30 months. But basically, you can see it's a team from 3 institutes, from Georgia Tech, and then from Larry's group in Cape Rogers, and of course, we also involve Ohio State, and later Keith Johnson went to Berkeley. He took John O'Hara's position at Berkeley. Okay, so now, and the funding, it involved Mary Harper and later Tanya Koraski. Now, so this is the ASAT paradigm. Basically, the idea is the main part is this block called Bank of Speech Attribute and Event Detectors. So this precedes all the processing. So basically, this will generate a set of events with some scores of interest. And it's not just one set of speech analysis, but we can explore many different speech analysis tools here. And then the output of this will be a lattice that allow us to interpret some of the events and then combine them. So there's something called an event merger that I will talk about later. And then there's also evidence verified that I don't have time to talk about today. But basically, you try to iterate between event detection and the evidence verification to go from low-level attribute events to high-level evidence like words and sentences and phrases. So it's basically just keep refining your hypothesis based on the set of knowledge sources that you may come up with. And so this can be iterative to go from low-level events to high-level knowledge. And I'll show you a more detailed picture right away. So this will be something that can go very extensively, that starts from speech. You have a set of speech analysis tools that give you an ensemble of parameters. Now, after, different parameters may be useful for different attribute detection, but you basically have this module that allow you to go from parameters to some linguistic notion that you can take advantage. So after this, you come up with an attribute lattice. And this lattice basically will allow you to go either from attributes to forms or syllables or other linguistic units. So there's this attribute to form lattice that, of course, can be arbitrary, that this can be form, this can be syllables, and can be other things. But the main part, of course, is that we like to go from attribute to words. And so, again, this will be a lattice. And then from this word lattice, of course, we can verify some of the words in the lattice to come up with your recognized sentence. But in the process, of course, you not only come up with sentence that you recognize, but also all the intermediate events like attribute and forms and words and maybe other things. Now, attribute, here I define them as, can be place and manners of articulation, can even be a word, can be speaker event, can be accent, signal to noise ratio, and other things like articulatory trajectory, something like that. So attributes can be very general, but we can use those attributes to help us interpret speech events and then link them between speech and linguistic events like words. Okay, so now I try to put in a probabilistic notion so that we have an ensemble of parameters at time t, and then of course you come up with a probabilistic lattice, attribute lattice, and then probabilistic form lattice, and then of course a word lattice, and later of course you have all the recognized events of interest. So this is very general. So now the first thing is the detectors. Now the detectors, of course, the notion of detectors is not new. When we talk about landmarks, of course, we are talking about detecting landmarks, right? And now, for the speech attributes I have in mind, we can actually use many different ways of, speech analysis. So for instance, we can have frame-based and segment-based detectors. We can have some specific parameters, like for instance, many of you know about voice onset time is very important to discriminate between voice and unvoiced stops, right? So those are, some specific parameters that are definitely not MFCC, right? And then, you can bring in zero crossings and many other things to help you, for instance, for nasal discrimination. Now, some of us are looking into physiologically motivated processors and detectors. I don't have time to talk about this, but specifically, we had done some cortical analysis models to see how speech and cortical models react to each other. And this can be used for speech event detection as well. And then, of course, there are other things of interest. But I will mostly talk about this set of frame-based and segment-based detectors. So here is what Ken was talking about, that what do I mean by manners and place of articulation. So this is a set of manners that we've been using. So there are 6 manners: vowels, fricatives, stops, nasals. This is like semi-vowels and silence. So this is a detection curve that we design detectors, and we plot scores of detection versus time of the events of interest. So you can see this is a spectrogram, and then here are the vowels. In terms of the red one is the provided by experts in label, and the blue one is the output of my detector. And you can see the detectors follows the knowledge, the ground truth quite well, but not all the time. And so here you can see there's a false alarm here, and then here there's something happening here. But most of the time they follow quite well. So I'll give you some notion that how well we do in timid later on. And then, of course, here is the silence. So this is the beginning and the ending silence. So this is done with neural networks. Yeah, but you can have any kind of detectors as long as I can scale the scores between 0 and 1, and I'm in a good shape that I can put some threshold and then decide if I want to detect a particular event of interest. No, yeah, no. So you will see that stop is a difficult one, but in some situations, if we stick with frame-based detectors, so this is frame-based, based on every frame. But once we bring in the segment information, you'll find that it's better. Yes, Rick. That's right, yeah. It's an easy way out, but we just want to see how well it works. Yes? So far, we have not, but if you want a threshold, you can say, hey, I want a threshold of 0.5. And then anything beyond 0.5, I say I detect something. Anything below, I say, hey, it's not there. Then you have false alarms and false detection. Yeah, it's based on a way of describing the events in terms of scores between 0 and 1. So it can be posterior probability or anything that's fit in that notion.
In this specific case, you said these are neural nets, and they have just two categories, vowel, non-vowel.
Yes, yeah, that's right.
Really are the posterior probabilities of vowel.
So in some sense, yes, but we can be more general than that. Yeah. Okay, so now how well does it go? So baseline performance is using frame base. So this is the frame in terms of the frame accuracy or frame error rate. So you can see that vowels in terms of frames, it's about 9% error. And then, they are, for instance, stops are hard, like what Ken was saying, and then approximate those semi-vowels are hard. On the frame level, now, if I use HMM, yes?
So that's a decision based
On the thresholding, yeah.
only on the content of the single frame.
Yes, that's right. Yeah, no, just one frame, yes. So this is frame base. Oops. Frame base result. Now, if I, instead of using neural network, I just use HMM. I know how to design an HMM for detectors. So basically what I'm just doing is that yes or no, right? Just, Then you can see HMM, they have segment information. So actually HMM does very, very well compared to frame-based approaches. And here, I'm just using MFCC, nothing else, just MFCC. Now, if I use discriminative learning to improve my HMM, then you see that this is in the range of interest now that we are on the average over 95% attribute recognition now. So this is for the manner of articulation. Here, so this is the number, based on the HMM model, and then I use discriminative training, on top of HMM, and you can see that they do quite well. Just discriminating yes or no, just two classes, yes or no. Yeah. Now the next thing is that, okay.
So would the error rate be very different if you matched precision recall?
Yes. Yeah, well, I mean, in this particular case, because there are two events of interest, so it will be, numbers that's around this number that I'm giving, that those are the error rate.
0.5 actually means probability of 0.5.
Probability of what?
The detection threshold of 0.5, can we interpret that as probability, or is just some...
This is the error rate. We are interpreting this as error rate detection by combining false detection and false alarms together, and that's the combined error rate.
I'm just asking about the way you set the threshold. It's not so important.
The threshold in this case is 0.5, like what I said earlier. But on the segment level, it's the entire segment. So it's more robust than the frame-based detectors.
At any rate, in the full system, the detect, you're not thresholding at all.
No. Later you'll see that this is just for showing how well you can do. Yes. Yeah, Jack. So.
Verify what data is this
Timid. Yes, this is timid. Clean data is good. So later you'll see that it's not as well for noisy data. So you'll see. Now, so going back to language universal detectors, this is earliest the experiment that I have done. So this was done by a student, my first student from China. So I asked him to do this experiment when he was still in China. So I said, hey, you have some Chinese databases. Why don't you use them to design those detectors? And then I want you to speak a few English sentences into these detectors and see what you get. And then, so this is one of the sentences. And you can see that this sentence has 4 stop sounds. and 2 nasal sounds, and then a number of vowels. So, overall, the stop sounds are detected quite well. Nasal sounds, there are only 2 nasal sounds in this case. Vowels, yes. Now, there were 2 misdetection here, false alarms. So those are lip smacks because this person doesn't speak English very fluently. So he ended up making mistakes here and at the end of the utterance. So that actually is our first experiments about language universal detection and say, hey, can you train with one language, for detectors and then detect something for a different language? So later you'll find more experiments about this. But still, we're talking about clean data, so it does quite well so far, right? Now, here I don't have a formal evaluation, but later you'll see some formal evaluation about how well they do in cross-language attribute detection. Okay, so now the second part is this something called event merger. So basically, this is the first step of knowledge integration, that we say, hey, we have some basic events. Based on some knowledge sources, we want to combine them into higher level events. So for instance, we can say we can merge multiple hypotheses so that you can have, for instance, you say, hey, I have a nasality activity and vowel activity, so can I conclude that there's a nasalized vowel somewhere? So those are the one type of combination. So that involved with something called combining spatial events. And the other one, of course, is combining temporal events, like you have a sequence of events that you want to combine them together. For instance, combining phones into words, and of course you have pronunciation variations, but this is pretty much like, I have phones, and can I design a word detectors based on phone detection? Something like that. And of course, you can imagine that if I want to push it, I can say if I want to build a 20,000 word Wall Street Journal recognizer, then I can build 20,000 keyword detectors. And then will that work well? So we have some experiments on that. I don't have time to talk about that, but if we can do that, I think we solved the problem already, right? I mean, we can detect any word. If you can specify a word, and you just go to Radio Shack and buy 10-digit detectors, and you have a digit recognizer already, right? So I mean, they're all already made for you, and you can just buy them. But of course, we are not there yet. And, so the event merger is, in some sense, is something like this, that we started with a signal, and I think in perception, we have something called A1 and A2. So I don't know how it related to speech event merging, but you can see that we can start with probability of those attributes. And then after some merging, we end up with some meta events. For instance, the meta events can be phones. And then, of course, you can keep going on. It depends on how much knowledge integration you want to bring in. Now, I have to admit that this is the area we work on the least, because we were relying on Keith Johnson to help us, but he ended up going to Berkeley, so we did not really have a lot of his contribution in our work. But this is an area, of course, we will need a lot of help in the future. Okay, so let's talk about some applications. So I think now, I was talking to a few old friends here. They're talking about resources rich versus no resources instead of resource limited, for instance, speech recognition. But this is one notion that we know today how to do resource-rich speech recognition. I think a lot of companies already have systems out there. But if you talk to Microsoft and IBM, they will tell you that we don't know how to do well for some of the resource limited languages. So what can we do? And you can imagine that, the performance of this resource limited or no resources language are not very good, and there are plenty of work to do. But what I was looking into is, can we use attribute for some of this effort? And what kind of level of performance can we get? So before we push that far, I had let me skip this one. But let me share one interesting story. So I had I was in Microsoft one summer to do a project on universal speech recognition, and so I want to push the idea of attribute-based speech recognition, and they push back and say, no, you cannot do it in 3 months. I said, I know, but I want to see, what kind of result we can get. Instead, they asked me to do a project. So this is a paper published in ICASS 2009. So at that time, we were trying to compare the state-of-the-art multilingual ASR. So this was a paper put together by CMU. And at that time, they have a few conclusions that, to me, it was very strange. So the first conclusion was that they have this notion of language-specific acoustic models. It gives them 16% errors on 90 hours of training data. And then they have some notion called language adaptive. Basically, you go by taking a big model and then do adaptation to a particular area. And then they say, oh, we are getting about 19.6% error based on 1.5 hours of adaptation data. So it looks good. But then they also have this result that when they train a language universal model, they end up with 70% word error with 200 hours of speech. 200 hours of speech training data. So that to me is very strange, because if you cannot do better using language universal than language specific, there's something wrong, because you have more data. That means that you are not sharing enough among different data sources. Yes? In this case, I believe it's 10 different languages, or maybe, it's in that ballpark. So we did a similar study at Microsoft with one student from University of Washington. And, I stayed there for 6 weeks, and he was there for 3 months. And during that period, we used probably all the computing resources at Microsoft. We end up with a set of results that's very interesting. We basically have a language universal model that's about 180 hours. And then language adaptive data that in some cases you have up to 24 hours of data. And then we find that we can outperform language-specific modeling, meaning that if I have more data, I should do better. And that's, agree with our intuition. And, if you're interested in more detail, I can share with you later. But of course, one thing that's most important, I think that's different from our study with this previous study, is that we try to be careful in defining the set of universal forms. So this is the case that we have 8 different European languages. So the set of forms are closer, but we have to do some clustering in order to reach to a set of units that may be more shareable than other definitions. So now, these 2 studies basically give you some idea that, hey, we still have a long way to go, because based on similar data, we reach different conclusions. Yes. Yes. Yeah. Oh yeah. So yeah. Yeah. So we have language adaptation. Basically, we use the same notion. like what they have there, and actually language adaptation outperform language specific, like what we expected, right? So that I think it's at least agree to some of our intuition, like what I was saying earlier. So now, of course, in the future, we like to extend this to instead of phone definitions, because it's kind of difficult to rely on a universal set of phone definitions. And so we're hoping that maybe there's something more fundamental, like attribute, that can help us define a universal set of fundamental speech unit that will allow us to go beyond different languages. So that one I will talk a little bit later on. Okay, so let's talk about how to build this. I think I talked about this already, but basically we need to have overall speech database and transcription. We also need a common definition of fundamental units. For instance, in the case of a study done at Microsoft, we're using IPA-based definitions, and the lexicon was defined with a unit similar to IPA, International Phonetic Alphabets. And of course, this description is very important, universal phone description. And it turns out this is not very easy to come by. I think if you talk to different people, they will tell you something differently. But it turns out there's a many-to-one and one-to-many mappings. Some units, they will map into different units in different language. And then, some units, they have multiple definitions across different languages. So some kind of additional processing may be needed there. Okay, so now, what are the research issues? You can imagine CMU's result and our results are very different. And we are all based on some form of IPA. So can we do different definitions instead of IPA? The list go on and on, but my interest is to say that can we train a model, a universal model that once, and we don't have to revisit them? Can we train that? If that's doable, then we just train one and just do adaptation, then we are done, right? But of course, many of the problems we talk about have to be resolved first. But with this in mind, maybe we can look into different kind of units, and that's the attribute units that I was going to talk about. So that's train once and for all, right? Now, so the attribute such as place and manners of articulation seems to be more common and shareable across languages. If you look at Hindi, for instance, Hindi has a set of phones, but the set of place and manners of articulation seems to be, similar to what we use for English, for instance. Maybe you have some arguments here and there, but at least that's probably more universal than phones. So I would talk about cross-language phone and attribute recognition, just to give you a notion that the stuff I was talking about, language adaptation and language universal, can be better than language specific. And then I would talk a little bit about our recent effort on language-based spoken language identification, attribute-based spoken language identification, meaning that you can do language recognition without defining phonetic units. And then we can share the definition among different languages. And if you push it, you can actually do language identification without speech data. If we agree that this notion might be interesting. So that's my second application. And, we will talk about, I think we, are we? I think I need probably about at least 20 minutes. Yeah, okay. Okay, so the first one is speech detectors. I think, typically what we have is that we have the signal, then we go through different different signal processing, and then go through different detectors to come up with this probability of the speech events of interest. And the nice thing about here is that the detector can come from different time frame. For instance, if you're interested in voice onset time, then it doesn't have to be processed every 10 milliseconds, for instance. Now, so if we want to do attribute phone recognition, we have to do one more thing. That's this guy in here, the attribute to phone mapping definitions. This is actually difficult. But what we have here is that we are using this part. We actually use a neural network to do that because it's an easy way out. But I'll share with you some results later. But we have a couple of papers in this area called attribute-based phone recognition and phone modeling. Now, event merger basically is that we started with, remember, this probability of the signal given all the events of interest, and then we try to combine them with a neural network to come up with this attribute to phone mapping, so probability of different phones. And then after that, you can just use the conventional Viterbi decoding to come up with the phone sequence. And so this is what we use for continuous phone recognition. So neural network here to come up with a posterior probability of different attributes, and then neural network here to merge them to produce probability of different phones. And then after that, you do Viterbi decoding to come up with the sequence of phones. I think some of the studies here are using similar approaches. Yes, Ine.
One frame of sequence in and one frame of posteriors out.
Yeah. Yes. So one frame here and one frame out. And you have, so this is very much like the posteriogram that you have set up in some of the applications. Remember we're talking about this, language universal. I was hoping that this can be more language universal. And, after talking to Samuel, and it looks like there are some common interests here. So this is the merger that I was talking about. So the neural network we have from attribute to phone. So basically, this is one frame of input, and then you have yes and no probability, and then you go through a neural network to come up with, phone posterior yes or no of the phones, and then you just combine them. By data, by some data. Mm-hmm. Yes, yeah. So this is something, this is like an example. So this is done by a student of mine. So basically, you can see that those are output of detectors, right? So the green part means there are some event detection related to the particular event, like, coronal, and then here silence, voice, events, anterior events, vowel events, and so on and so forth. Now, they are not 100% correct, of course, but we can combine them to come up with, combine the events of those green islands and then come up with probability of some of those events. And then, of course, here you have a dental event for the stop sound D, and so on and so forth. So that conceptually, and now the time scale is not completely right, but basically conceptually is that the signal is now converted into some scores related to different manners and the place of articulation, and then you can combine them into scores of phones, and then after that you can do phone recognition. Oops. Okay. Yeah. Okay. So let's talk about results. We are using an OGI multilingual story corpus because I think I shared this story with some of you already. We cannot use Call Home because Georgia Tech was not a member of LDC when Call Home was published. So it was very expensive and I cannot afford it. So we just use this particular phone set, and we're fighting very hard with the LDC with no results. So, but anyway, this is not a very good database, but at least we can get something done. So there are, in this particular case, there are 21 events of interest already labeled. So those are the set of events, including place of articulation like anterior, back vowel, continuous, coronal, and so on and so forth, plus some like fricative and approximant, nasal, stop, vowel, those manners of articulation. So 21 events, 21 detectors. Now the 6 languages are German, English, German, Mandarin, Spanish, Hindi, and Japanese. The database is very small, so it's a training part is about on the order of 1 hour or less for each language, and testing is about, again, very small. And if you look at training individual data sets, so language-specific phone error is in the order of 50%, so this is not very good. Now, if we train one set of detectors based on all the data, then you can see the language universal phone error is here overall, and it looks like we are always slightly better than language specific. So it looks like some kind of knowledge sharing can be done between different or across different languages. Now, specifically, let's look about some of the attributes. So this one, the setting is that we have the solid line detectors trained with Mandarin for some of the attribute down here. And you can see that the range of performance goes from low 40s all the way up to 90s. So depending on the different events of interest, you have different attribute detection rate. Now the other different dots were based on different attribute trained with different languages. For instance, this purple magenta dots, Spanish, is basically all the detectors were trained based on Spanish. So you can see cross-language attribute detections are, do not do as well compared to language-specific attribute detection. But in some cases, we see Spanish detector does better than Mandarin detectors. Not a lot, but you can see occasionally cross-language detection can perform well.
Let me ask you a question so that I can interpret the better. Each of the columns, let's say fricative or voice,
Yeah.
it's a binary decision.
Yeah. Yes.
And so let's pick something like nasal.
Yeah.
So it's a binary decision, nasal or not.
Yes.
Any language-specific detector.
Yeah.
That, let's say 63% or something.
Yes.
The correct language detector.
Yes.
Cross-language detector.
Yeah.
Are a little worse.
Yes.
What is Chan's performance on nasal?
What chance? Chance performance below 50%? Huh?
No, meaning if I just market with the dominant class, most frames are not nasal.
Yeah,
You probably get 60% too.
we are not using that information, right? But vowel is probably more interesting because, for instance, in Japanese, 50% of the sounds are vowel sounds.
Right. So all I'm trying to figure out is whether how much about random is this? Or baseline, whatever.
Yeah.
The majority class.
The majority class, I mean, this is you mean the random guess? Yes or no?
No, just guess the more likely label all the time.
More, remember here is yes or no.
Yeah, that's what I'm saying. So
Yes.
whatever is more likely, if a frame is more likely to be vowel than not, then call everything a vowel.
Uh-huh. Oh, yeah. Yeah.
Call everything not a nasal.
I don't have the number, right? But, I mean, vowel, you can see that, for instance, in Japanese, 50%, right?
Yeah. No, I think the
Yeah.
vowel performance is very good. I'm just looking at the
Yeah. Mm-hmm. Yes. So you can always say no, and then you will do very well for some of the attribute that has very little data in here. No, yeah, we are not looking at that.
So I just got confused. You said Japanese, which is the yellow.
Yeah, Japanese specific. Remember here we are using Japanese detectors to recognize Mandarin sounds.
Follow Sanjeev's suggestion and just say, okay, since 50% of the sounds in
Mandarin.
Japanese in Mandarin,
Uh-huh.
So the test is always Mandarin.
Yeah, the test is always Mandarin in this case. Yeah.
the test is always
Yeah, here, because we were just trying to see, if you train Mandarin specific and then non-Mandarin, specific by cross-language attribute recognition or detection, how well do you do?
So do we have any knowledges in the room know what fraction of Chinese sounds are vowels?
50%?
I think 50 is not a bad guess.
Yeah, syllabic, right? Yeah, syllabic, right?
Well, if you say it's 50%, then the fact that vowels are the very last one, it's up to 90%.
Yeah, vowels are not by chance, of course, yeah.
But
Yeah.
I'm thinking it's nasal.
Nasals, there are some of the events that happen less.
I would say 30%. It's not nasal, I'm at 70%.
It's Sanjeev was talking about if you impose some prior information, can you do better, right? So here we're just, giving you the raw numbers, the raw numbers. Now, the other one is language universal attribute recognition. So you can see now we have one model of attribute trained by 5 different languages. And in here you see in more situations that the language universal detectors actually does better than language-specific detectors. So there seems to be something there that, of course, this is not a very good database, so, what we are doing here maybe cannot be extended. But I think when I was talking to Samuel earlier, it looks like this is an area of interest, a common interest. But again, here, this is cross-language and trying to see if we can do cross-language attribute recognition and then language universal attribute recognition. And they are an important factor if we want to share knowledges across different languages in order to do universal modeling, right?
So let me again ask another question. Is this the same lesson as saying that if you want to detect the speech from one speaker, then you can either build speaker-dependent models just with the speech of that speaker.
Uh-huh.
It will be worse if you use a speaker-dependent model from another speaker.
Uh-huh.
And you will do better if you do a speaker-independent model with speech from lots of speakers.
Probably not for all the events, but at this level.
In case of core basic word recognition using HMM,
Uh-huh.
this is let's call it the, I don't know what's the word, the community of folklore or whatever. This is what the community feels.
Uh-huh.
And is this an instance of the same phenomenon?
Well, I think probably some at the attribute level, probably we can claim more about this, and then at the form or word level.
So what you're saying here is that instead of building a language-specific attribute detector
Yes.
is a language independent.
Oh, yeah. That's what I'm getting at, yes. And so that's where, we remember the title was about language universal acoustic modeling, right? So we were trying to see how far can we push the envelope, right? And how far can we go if we are giving data from many different languages, right? What can we do with it? And so this is one application. Now here, of course, we are using only 6 different languages. So they, probably, we have to do more in this area if we have a better data set. Now, the next one is cross-language phone recognition. Again, this is not a very good database, but we say, okay, suppose I have detectors trained by German, and then the attribute of phone mapping trained by German, then the phone error rate, is 66%. This is very high already. And then Mandarin, English, Hindi. So the best we have is Spanish, because Spanish and Japanese, they have 5 vowels, similar 5 vowels. So you remember 50% of the Japanese test data are vowels. So this is the case that we say we have not seen Japanese at all, but we use other languages and then do cross-language phone recognition, assuming that we can train a system for Japanese. What happened? Right, so, and the best we can do with Japanese, you will see, by doing language specific is, oops, I think I have something. So the best we can do with Japanese was about 38%. So we are far away, right, using Spanish or using other things. So Spanish, we're getting about 49% phone error. But suppose we train detectors with 5 different languages and then use the Spanish attribute to phone mapping model, we are getting about 47%. Better, slightly better. So you can see the more knowledge we bring in, even we have not seen any Japanese data, we can do better by doing language universal modeling of the attributes. Now, I can share with you, actually, we try to say, hey, suppose we take a very little Japanese data to help with this, and then we do better. So having seen some data will help, but cross-language speech recognition is a very big push right now that I think we are still far away from there. Yes?
Could I suggest an additional number to add, and that would be to take 6 hours of Spanish.
Yes.
Replace the LU5.
I understand, yeah. Uh-huh.
And I'd just be curious how close you get to that.
Remember, in Japanese and Spanish, the set of phones are different. So there are some phones that's in Japanese that's not in Spanish, and the other way around. So
This is tested on Japanese?
yes, only on Japanese.
Oh, sorry.
So it's cross-language or basically we try to see if we have no test data from one particular language, how well can we model that particular language? So that's what I mean. So all the results here are based on testing Japanese without seeing any Japanese data. Okay, I think I'm in trouble because we are over. But give me 10 more minutes. The last part, I promise to be more interesting. Okay, so spoken language ID. So we've been doing quite some joint effort with a group in Singapore. I think some of you know about the group from Singapore doing language identification. And so we bought into this notion that there's this front-end utterance tokenizer followed by a back-end vector space model that allow us to design a language ID system. So it looks like something like this, that we start with spoken utterances, and then we have a universal acoustic recognizer as a front end, and then we convert this into spoken documents. And then after that, we try to convert the spoken document into something like a document vectors, and then from there we can model document vectors from different languages to come up with recognizers or classifier for different languages. Now, of course, the transcription, the tokenizer can be different, and the document can be different, but I'm going to talk about one specific way we do things by taking something from information retrieval. This process is to convert spoken utterances into text, and then after that, the rest of them is just text-based systems. So it turns out this is quite powerful, and our first study was on this particular one based on the Shannon's notion. I think many of you have seen this paper probably. This was done in 1951. Shannon did a study on entropy of English, and basically he just used, by count all the events by hand, and then he was able to come up with this notion. The first one is easy, the entropy with no information about the alphabet. So basically there are 27 events, all the 26 English letters plus space. So there are 27 events, so log 227 is 4.76 bits. If I give you the previous digit and you try to predict the next one, it's about 4 bits. Shannon's number. And then if I give you if I give you the first order means that which digit occur more often, then you get 4 bits. If I give you the previous digit, previous letter, then you get 2.8 bit. So this is based on one-step prediction. Now, if you give 2 letters, then Shannon cannot do it because there are just too many. That if you count it by hand, it will take forever to do. But my student in my class, they can do this. So I just give them, Wall Street's, give them timid sentences. And then what they came up with is 2 bits. If I give them 2 letters to predict the next one, it's 2 bits. Now, if the other extreme is to say, suppose I encrypted all the letters, and then there are 2 different competing languages. Can you do language identification of encrypted letters? So one of my students did a project on this. If the input letter sequence is long enough, you can use it to do language ID, and then recover the original transcription. So
That's true for substitution.
yes, yeah. But what I was saying is that there's a lot of information in entropy. So can we do spoken language ID with this notion? So that's what I was going to talk about. So if you can have a common set of alphabets to transcribe or describe different languages, then based on the entropy information, you should be able to do language ID. So that's the thing. That the first thing is that what is the acoustic alphabets that we have to do. So that goes back to the acoustic segment model I was talking about, that we started by describing the acoustic space in terms of a small number of acoustic models, and then use them as universal acoustic recognizer or tokenizers. And this is kind of interesting because we used to have this notion using phone models, but this has nothing to do with phone definition at all. Everything is done with acoustic definition, and here are the results. So suppose I use 32 units and then just count the occurrence of the individual unit probability. Then based on the 12 language in the 2005 NIST test, we get about 40% error if I use only the unigram. But if I incorporate bigram information, meaning co-occurrence of neighboring letters or units, then it dropped to 32%. And then if I use 3 of them, then it drops to 28%. So here the features are latent semantic features in terms of those transcribed sequences of letters. So you're just saying that now, instead of looking at acoustic signals, now you have a sequence of letters. Each one of them, basically each utterance is converted into text and transcribed by the sequence of acoustic units. And then with 32 units, it's not very good. Now, if I go to 64 units, then here it's getting more interesting now. It's now about 19% if I have bigram information. If I go to 128 units, I'm down to about 14%. Now, here I cannot use trigram because the vector size is too big, because if I use trigram, I need a vector size of 128 times 128 times 128. So we stop at bigram. But it's just giving you some idea about this entropy information. What can we do? So, and then if we increase this 128 to about 256 units, then we get about 12%, 12.5% error. So, yes, they are error rate for language ID, language identification of 12 languages.
How long are the others?
This is 10 seconds. 10 seconds, yeah. So, now, the point here is that we were not using any linguistic definition, but just the co-occurrence of units. It will give you something quite interesting already. So, now, those units are based on acoustic segment models, so there are no linguistic definitions. More recently, we say, hey, suppose we use attributes. What happened? So now you have some linguistic notions. And it turns out, if you go back to the OGI database, we can use it for language ID also. And if you use text transcription only, you get 100% language ID. Yes? You know latent semantic indexing technique?
But, I mean, you're using it as output of your universal.
Yeah, so the universal set of units are those 128 or 64 or 32 units.
So do you have access to the oracle transcription over those?
No, there's no transcription. Basically, just starting from scratch. You say you acquire those acoustic alphabets.
I was wondering if you could show some numbers for the oracle experience. The phone transcriptions were not noisy.
Phone transcription? What do you mean?
You don't have transcription, but I mean, if you had, you could use them to see, using these co-occurrences on the true transcription.
Oh, I think many people use that already. So for me, that people who are interested in that, they can do that experiment. But I'm more interested in using universal units that that doesn't rely on a lot of phone transcription, right? So this is based on acoustic unit that has no transcription at all. Okay. So now, let's use attributes. So for attributes, we have something like this. So we started with an utterance, and every utterance is transcribed into something like this: silence, vowel, fricative, vowel, and so on and so forth. Now remember, in our experiment, there are a lot of transcription errors. Now if I have perfect transcription, I get 100% language ID for all the testing utterances, that we set up for language ID. But here we are talking about very high transcription errors. But we can use this transcription to build language, to build latent semantic indexing vectors, like what I talked about earlier. The same way like what we did with the acoustic segment units. And here, based on this information retrieval technique, that we basically build a term document matrix, and for every utterance, and then build the language recognizers accordingly. So here are the transcription, attribute transcription accuracy that we can talk about. So suppose I use context-independent models. Then for 6 manners, we are getting about 38% error. And if I use right context models, then I get about 35% error. And of course, you can have different variations, but we are talking about for manners of articulation, you are getting about 26% transcription error. And then for place of articulation, we are getting about 36% error. So those are very high transcription errors here. But it turns out that the construction for language ID is quite robust. So I'll show you the language ID performance. So language ID performance, we can see that suppose, so I have, in this case, 6 manners of articulation and 10 place of articulation. So I can use, remember we talked about bigram, trigram. In the earlier case, I cannot build trigrams. But here I can build 4grams because the number of units is very small, so I can build a very long vector. And you can see that the equal error rate drops as I increase the number of singular values in my term document matrix. But it's saturated at about an equal error rate of about 18%. Using place of articulation, manners of articulation. And if I use place of articulation, then this is what I get, that I end up with about 20%. So they are not looks like they are, the transcription error is high, but the language ID equal error rate seems to be reasonable. Now I can combine them also. Remember, here there are 2 sets of universal units, so I can combine them. So when I combine them, then I find that by combining, here is using context-dependent models. So here I'm getting about an equal error rate of 15% for manner, and about the place is about same thing. Place and manners of articulation, the error rate is about 15%. But if I combine them, then we are getting about 8% equal error rate by combining place and manners of articulation for language identification. And I have some numbers done by the BUT system. So, for the current construction, we're doing better than the BUT system. But I think the interesting part here is that place and manners of articulation, if we use it right, then based on text, you can actually train a language recognizer already. So, yes, Jack. This is OGI again. Remember I said I don't have call home, so we just use OGI.
This is not a NIST with...
No, it's not. This is the 6th language OGI database. We love to use the NIST construction. Yeah. This is not NIST, but this is the OGI construction. No, we cannot, but we'll try to migrate our system to the NIST case. But again, what I was trying to say is that attribute like manners and place of articulation is actually quite powerful if we can use a sequence of such events for language ID. For instance, we know Japanese is syllabic, right? So it's about CV events happen a lot in other languages. So if we use that information for language ID, some of them can be done quite well. Okay, so I think I'm already over quite a bit, but just quickly summarize. So I talk about universal speech attribute modeling, that try to take advantage of some common shared knowledge that can be used across many different languages. And then I talk about language universal modeling can be better than language specific modeling if we do it right. And I also show some cross language phone recognition experiment. They are not very good yet, but it seems to be, if we do it right, we can do phone recognition without speech data, without speech training data. And the other interesting part is this attribute spoken language recognition, that we just use small number of attributes to allow us to model languages without using so-called phonetic definitions. And we just use the engram features, just co-occurrence of events of those attributes. And they, they give us some information like what's done in Shannon's entropy study, and we can take advantage of that. We're able to use this to get very good performance for the OGI database, but definitely not for the NIST language ID evaluation. And then it's possible that we don't need training speech for some languages that we cannot really get language speech training data to train language classifiers for some of those languages. And so we can extend this approach to resource limit languages, for language ID. I just want to say one last thing is that recently we actually had our final application for the ASET data. We were able to do a large vocabulary speech recognition system using bottom-up detection-based systems. So we submit a paper to ICASP, and we'll share more information with the community for our study later. So you have already the set of slides, so there are a lot of references here. Thank you very much. I think many people collaborate with me on this effort. So, and we,